Alright, today we'll be looking at grade 12 again, physics part, which is photoelectric effect. I'm going to try by all means and summarize this particular topic for you guys so that you'll be able to understand it. Now, as I always say, there are a lot of information that the textbook will give you, but I want to only focus on what is necessary and what is important for you guys. So let us get into it so that when we do the questions, you will be able to follow. Alright, now let us look at the first word there, which is photo. We are all used to that word, but in physics it means an entirely different thing. So in physics, that word, the photo, means a very important thing there. Photo means light in physics. So in that case, that should give you an idea of what we'll be talking about. So we have light and we have electrical energy, of course. So in that case, remember with our first video on electrodynamics, we were producing electrical energy using the mechanical energy. But we all know that that is not the only way we can get the electrical energy. We can get electrical energy directly from light. That is why people use the solar panel and all those things to get light. So, meaning that we need to understand the behavior of light or what light is in general. So, in that case, there have been so many discoveries about light. We have studied light in grade 10. Then we were talking about the dual nature. We were talking about the dual nature of light. The dual nature of light. The dual nature of light means that light has two behaviors, guys. We all know that you have been told that light can be seen as a wave. Light can be seen as a wave because of its ability to bend, its ability to reflect. All those behaviors gives light a wave nature. So that is why here we are saying light has a dual nature. Dual nature means that it has two behaviors. The first one, which is the wave nature of light. Then the second one, which is what gives us this particular topic, then it is the particle. Light can be seen as a particle. Perfect. So now let us look at that dual nature of light. We already see that light can behave in two different ways. It behaves as a particle as it moves, because we all see, we can see light traveling in a straight line. That is because we see light as a particle. Then its abilities to reflect and to diffract, or just in case just to bend, it gives light its the wave nature. So I'm just going to say a little bit about light as a wave, then we will now focus on this one, light as a particle, because that is what we want to be looking at. So now, light being a wave has so many things that we can be talking about. Firstly, let us look at light as it moves here. We are going to have the speed of light here is equals to the frequency multiplied by the wavelength. The frequency multiplied by the wavelength. So meaning that the wave the wavelength there actually tells us what it is a wave, because you can only have a wavelength from a wave. So in that case, this is what is telling us. Therefore, now we can see now that there should be a relationship, because this is the speed of light in a vacuum, which is always given to be the rate times 10 to 3 times 10 to the power 8 meters per second. Therefore, this one being a constant, it gives the relationship between the frequency as well as the wavelength. Okay, now the frequency of a light is the one that tells us about the energy, which we will be talking about it under the particle. Now, in that case, we know that we have the different types of waves. We have different types of waves, or that are on the electromagnetic spectrum. You can see from them we have things like radio waves. If you know the electromagnetic spectrum, I'm not going to write all of them here. We have the radio waves, we have the microwaves, and then lastly there we have the gamma rays, and then as well as the X-rays. All those particular things, and then the most important one I want to talk about there, it is the visible light. You can see your spectrum in grade 10, we talked about the spectrum. Therefore now, the visible light is the one that allows us to be able to see different colors, to be able to see, because light reflects from an object and then into your eyes. That is how we are able to see. Now, under the visible light, we have so many colors. Those colors, the rainbow colors. I'm not really good in differentiating the colors, but we have red there, we have orange, we have yellow, we have green, we have all these colors. Some they know it to be something like that. These are the colors that are in a rainbow. Now, what I want to explain them is the relationship between the frequency and the wavelength. Therefore, now, if a red light is shined on a material, I'm actually getting ahead of myself. Now, if I shine a red light compared to a blue or indigo or violet light, I can see that the wavelength of this is going to increase as I move from my right to the left hand side. So meaning that on this side, the waves on this side, they have the smallest wavelength. So if I were to look at the wavelength there, the wavelength is going to be very, very small. So the wavelength increases as I go towards the right, and then the frequency increases as I move along to my right. So this is what you can see in terms of the visible light and all other waves. So these different waves, they have different frequencies, they have different wavelength. So in that case, we can see now that the wavelength is going to increase from the gamma rays going backwards to the radio waves and the microwaves. So that is what the spectrum tells us. It arranges those different waves according to the increasing of their wavelength and increasing of their frequency. So light that is strong, a light that is strong has a higher frequency. So meaning that a powerful light has a higher frequency and then it has a smaller wavelength. So that is the relationship between those frequency and the wavelength. So meaning that, guys, if you are given the frequency of a wave, you can always convert your frequency to what? To the wavelength, and vice versa is true. So meaning that if you are performing any calculation and it happens that you are given the frequency you need the wavelength, you can do that by using the light, the speed of light there in a vacuum to be the frequency multiplied by the wavelength. Now, I don't want to dwell much on the behavior, on the wave behavior, because our focus is on that particular thing, which is a particle, light as a particle. So this particular thing you can revise light as a wave from grade 10. So now let us get into the particle behavior, which is actually the most important thing. All right. Now the observation of on how light is behaving is able to travel in a straight line tells us that light can be seen as a particle. So in that case, if I'm having my light shining on something in a straight line like that, what do I notice then? What do I notice in that light? I see some small particles there. Some small particles in that particular light. Now, that observation is very, very significant for us. So now we see that when a light is shined onto an object or onto a metal, we can see that inside that light there are small particles. And now those particles are what we call the photons. Those are what we call the photons. Now, people prefer to call this the energy carrier. The photons are the energy carrier. You have different ways. Some they say a photon is a package. Is a package of energy. Is a packet of energy. That means is a packet of energy. Let me just use that energy. Okay. Now, some they prefer to call this a quantum of energy. Now, guys, what do we notice here? What do we notice about what I'm trying to write there? These particles are called what? The photons. These are the photons. Therefore, now, what do we know about the photon from now on? Is that they are associated with what? With energy. So, these smaller particles, they carry energy. That is the most important thing. That observations change how we perceive light. Because now we realize that inside a beam of light there are particles there. Those particles are called the photons, and the photons are actually energy carrier. Therefore, now what do we see here? Now, this energy of a photon can now be calculated by Einstein's equation of, say, energy of a photon is equals to the Planck constant multiplied by the frequency. The Planck constant multiplied by what? By the frequency. So what do we find out here? This is the energy of a photon. This is the energy of a photon. Meaning, guys, pay attention on this one. Now, when I was talking about the light of different colors, they are going to have different frequencies. Are we together? So, meaning that the particles, which are called the photons, are going to have different energies depending on their frequencies, depending on their colors. Are we together? So we are saying now, we are not saying rather that the photons have the same energy. No, that is not what we are saying. We are saying the photon's energy is dependent on the frequency. And then the frequency is dependent on the color of the light. The red light will differ with an orange light, will differ with the violet light. So we are saying now the energy of a photon is calculated by the Planck constant, the Planck constant, the Planck constant, and then that is the frequency. That is the frequency. Now, what do we see now, guys? Is okay. Let me touch on this one. This one is a constant. Is always given in the formula sheet, or I mean rather in the data sheet. You don't have to worry about that. Which is equals to 6,63 times 10 to the power minus 34 joules per second. So that is what we are going to be having. All right. Now, the frequency, we all know our frequencies are measured in hertz. The energy is going to be measured in what? In joules, as always. Okay, therefore, now this is an important discovery that talks about the photoelectric effect. Now, we have a light which behaves as a particle. Those particles are called the photons, which carry energy, and their energy can be calculated by saying what? Energy of a photon is equals to the Planck constant multiplied by what? By the frequency. And guys, we have seen on the this equation of speed of light is equals to the frequency, multiply it by what? Multiply it by the wavelength. The wavelength is measured in meters. So in that case, meaning that instead of giving you the frequency, we can decide to give you the wavelength, and we say calculate the energy of a photon. Now let us see here. Let us take the frequency and then make it the subject of the formula. This is going to tell us that the frequency is equals to the speed of light in a vacuum divided by what? Divided by the wavelength. So guys, I'm going to take this and then put it where there is what? Where there is frequency. So we are going to end up having what? We are going to end up having energy of a photon is equals to our Planck constant, which is already there, multiplied by, now we, instead of frequency, we are going to put what? Speed of light divided by what? By the wavelength. Speed of light divided by what? By the wavelength. So, meaning our energy of a photon can be calculated whether we are given the wavelength or whether we are given what? The frequency. So we don't have to panic on that. Alright. Now with all this discovery that we have just discovered now, we can see that energy can be, is rather carried by the photons, and then they will carry different amount of energy. Now, what links these two things? The photons, or rather the light and the electrical energy. The light as well as the electrical energy. I'm going to try and put it here. Let me squeeze it here. What relate those two? The photons, rather the light and the electrical energy. Now, which is a very, very interesting thing as we are about to see. Let me start by defining something here. I want you to see something here, guys. That electrical current, I prefer to say electrical current is a charge. That charge, let me specify there, which is electrons in motion. I'm not saying you should define your current like that. We know current. Some they prefer to say current is the flow of charge. Some they prefer to call it the amount of charge that flows per unit time. So it will depend how, but don't define it like that. I just want you to see that electrical current is produced when a charge is in motion. Are we together there, guys? Alright. Therefore, what is going to be the relationship? What is going to be the relationship? How does the light end up giving us what? Giving us electrical energy. Okay, now let us get into this here. Let me draw something like that. This is a metal. That is a metal. It can be any metal, guys. It can be sodium, it can be potassium, as long as it's a metal. Now we know how electrons are arranged in a metal. Don't we know that, guys? We know that the electrons is just a pool of electrons that are surrounding that particular metal. So I'm waving my electrons there, which are bonded there by metallic bonding. So inside a metallic bonding, or the electrons are decolonized there. They are just bounded. They can be found almost at every space around the metals. That is why the metals are very, very good conductors of what? Of electricity, because of the arrangement of what? Of the electrons. Alright, so here you have your metal. It has electrons. Remember, these electrons, guys, they are not just free there. They are bound into the metals. There is a bond there. That is why we are saying there is a metallic bond. These electrons are bound to the metals. They are not just free as I'm just drawing them like that. Okay, now what is happening now is that we shine a light on this. We shine a light on, let me, now because I've already showed you, I'm going to use only one photon. Let me say that is my photon, which looks like a mitochondria. It's not a mitochondria, that one is a photon. Okay, so this photon now, we remember we said it does what? It has energy. It carries energy, and then that energy can be calculated by hf, or it can be calculated by h, speed of light, divided by the wavelength. Are we together there, guys? All right. Now, what do we now notice here? I have a photon, which is an energy carrier, which is going to be shined on a metal. Remember, the conservation of energy says we cannot create energy, we cannot destroy that, but we can do it, we can transfer it. So in that case, what are we going to notice here, guys? When a light is shined on a metal, the energy is transferred there, meaning that this photon is going to give the electron what? That energy which is there. Okay. Now, what we notice here, when the photon travels here, it is going to hit the metal, here. Let me put my electron there. It's going to hit that electron. When it hits that electron, it transfers the energy it has to the electron, not to electrons. One photon, one electron. That is very important. Put that in mind, because I'm going to come to that. One photon, one electron. So the photon is going to give the electron that energy. Now, when the electron receives the energy, it gets what? It gets excited, guys. It gets excited. The same thing. If you win money, you get excited. And when you are excited, what do? You jump. So in that case, let's look at that. The photon hits a metal. It transfers the energy to the electron. The electron gets what? The electron gets excited. Now, when the electron is now excited, there are some things that are going to happen there. There are things that are going to take place there. Let me create some space here. There are things that are going to happen. Remember, I said this electron is what, guys? Is bound to this metal. It is bonded to the metal. It is attracted to the metal by the force of the nucleus. So in that case, what do we notice then is a symbol. The electron, when it gets the energy, it gets excited. When it gets excited, it wants to do it. It wants to jump out of the metal. The electron wants to jump out of the metal. Are we together there, guys? So, but that can only happen if the photon energy is sufficient to overcome the bond between the electron and the nucleus, or let me just say, and the metal. So the electron is attached to the metal. So when it receives energy from a photon, it wants to escape. So when it wants to escape, it means that the energy that it has received must be greater or sufficient so that it can be able to escape that metal overcoming the energy that this electron is bonded to the metal. Are we together, guys? Okay, let me say that one more again. Now, when the electron receives the energy, it wants to do what? It wants to jump out of the metal. But for it to jump, it must have sufficient energy to overcome the energy that the electron is bounded to the metal. I think I put that in a nice way. Let me elaborate that. Okay, this is the photon. My hand is a photon. The lead of this marker is an electron. This marker is a metal which has bounded this. You see, the lead is bounded to what? To the marker. This is the photon. I'm going to the photon comes with its energy. It gives this to the electron. Then the electron tries to do it to escape the metal. But if I try to pull here, and then my energy is not greater or sufficient to the energy that this lead is attached to this, I'm not going to be able to do it to emit or eject the electron. So the energy that comes here must be greater than the energy that the electron is bounded to that. I'm using energy there so that I don't have to use the bond, because if I have to use the bond, we might miss something that I want to explain here. Okay, now the energy, if it's not enough to overcome the, I'm tempted to say the weight, I'm tempted, if the energy of the photon is not greater than the energy that the electron is bounded to the metal, then the electron will not escape or will not be ejected. Are we together? Therefore, let me now give the name to that. The energy that is needed for this electron to be ejected out of this metal, we are going to give it a name. We are going to call it what? The work function. We are going to call that the work function. Nice. Which is preferred to call it omega. Some people they call it omega. I just like to call it a small letter W, but it is an omega with a zero then, a smaller than a zero then, to show that this is a work function. Okay, what did we say, guys? The work function must be or should be the minimum energy, the minimum energy required or needed in order to eject an electron from the metal, to eject the electron from the metal. Okay, so that is called the work function. Now, the minimum that we need, for me to remove this lead here, I need the minimum energy to overcome whatever the energy that these two are bounded with. So, that minimum that I need is called the work function. Are we together? Okay. Now, let us get to something here. We know that the energy of a photon is actually dependent on the frequency, isn't it? So, it is dependent on the frequency. The higher the frequency, the higher the energy. The lower the frequency, the lower the energy. Are we together there, guys? Okay, so meaning that if there is a minimum energy that is required, there must be a minimum frequency. I think that makes sense, because the energy and the frequency, they are actually dependent on each other. The higher the frequency, the higher the energy. So if there is a minimum energy needed, there must be a minimum frequency needed, because the minimum energy will correspond with the minimum frequency. Are we together? Okay. Therefore, now that minimum frequency, we are going to call it the threshold. The threshold frequency. We are going to call that the threshold frequency, which is the minimum frequency needed. The minimum frequency needed to eject an electron or to emit an electron out of a metal. So we can now see the work function, which is we will ask you to define what a work function is, to define what the threshold frequency is. Okay, so these are some of the terms that you have to get familiar with. Alright, therefore now, what we see here is that now the work function should be related to the threshold frequency. So we are going to say the work function is equals to the Planck constant multiplied by the threshold frequency. Remember that H times F is an energy. What does that tell you? The work function is what? Is an energy. Are we together there, guys? Okay. Therefore, now the minimum energy corresponds with the minimum frequency. That is why here we say the work function is equals to the Planck constant, multiply it by the threshold frequency. Are we together? Okay. Therefore, now that we know this minimum energy and minimum frequency, let us get back to our diagram once again. So, if the work function is greater than the energy that the photon comes with, an electron will not be ejected. So, let me put some conditions here for you. Condition number 1, if my work function, if theta the energy of the photon, meaning that in this case there will be no ejection, the electrons will not be ejected. There will be electrons will not be ejected. Let me say no emission of electrons or no ejection of electrons. No ejection of electrons. Okay, meaning that the electron will remain there because you were unable to do it, to meet the minimum energy that is required. Are we together there, guys? So, if I come with a small energy and then this requires the energy that I have, I'm not going to be able to take out the lead, isn't it? Okay. The second one is this. If my work function, the energy, let me use the E then, if the energy, there will be an emission or there will be an ejection of electrons. There will be an ejection of electron. But the second part is that there is no going to be movement. The electron is just going to be lifted up. Yes, that is the term I'm looking for. The electron will be lifted up. The electron will be lifted up. Can you see that? So, if energy of photon, electron work function, what are we going to do? We are going to eject this electron or emit it. But now the electron will only be lifted up. It will not go anywhere because for you to move, you need energy. So the electron do not have any extra energy. All the energy was used to eject that electron out of the metal. Okay. Then number 3, which is where I am going to say a lot here. If my work function, if theta or it is less than the energy of a photon, what is going to take place there, guys? Now, meaning that the energy of this photon is much greater than the work function, which is the energy that is needed to remove that electron. So, let me put numbers so that you will be able to understand that. Let me say 20 joules. That is the energy of the photon. The energy that is required here, they only require 8 joules. Can you see that? So the photon has 20 joules of energy. The work function is 8 joules, meaning that I'm still going to have an excess energy that is left. So out of the 20, 8 is used to eject the electron. Then now the remaining, it is going to give the electron its kinetic energy. Is going to give the electron its kinetic energy. So I'm going to have my kinetic energy of 12 joules. Can you see that, guys? So the energy there, I'm going to have 12 joules. Now, because the photon has 20, we used 8 joules in order to overcome the work function, then the remaining should be used on what? On the kinetic energy of the electron. I always said it will get excited and then it jumps. When you jump, you are moving, then that energy is going to be actually used for the movement of an electron. Now see what is happening here. When the electron moves, what does that mean? We said current is when electrons do what? Moves. So the electrical energy is produced when electrons have enough energy in order to escape the metal and start to be in what? In motion. That is photoelectric effect. It's a phenomenon where a photon of sufficient energy able to eject the electron out of the metal, and then it gives it the kinetic energy. So that is going to be the photoelectric effect. Okay. Now, which is going to now tell us about this? We are going to write that and give you a new formula. The energy of a photon, let's see how it is used here. It is used to, number 1, overcome the work function, plus number 2, to give the kinetic energy to the electron. That is indeed the formula to calculate the kinetic energy of a compound. Now let me quickly do this one. We can now say energy is equals to our work function. We said is H multiplied by the threshold frequency plus 1/2 mv squared. We all know how to calculate the velocity of, the kinetic energy of an object. Now, guys, if you check this mass there, because it is the electron that is moving, what do we see there? We realize that the mass there, it is going to be the mass of an electron, which is always given, I think it's 9, something, then it is in the data sheet. So this, in short, this is photoelectric effect. Photoelectric effect is a phenomenon whereby photons of sufficient energy are able to do what? To eject an electron out of a metal and allow it to move. Therefore, when the electrons are in motion, they generate electrical current. Okay, so this is what I wanted you to understand. I will meet you again in the next video when I'm going to be explaining things like increasing the intensity, whereby Planck, this guy, the scientist who discovered this, was not able to explain why increasing number of photons does not increase the ammeter reading, or rather the current that is produced. We are going to meet on that one even when I explain the graphs. Now check for the next video on photoelectric effect. We will be explaining that and doing some questions showing you how to respond, how to take the information that we have discussed and put it in answering your questions. Alright, we'll meet again. I hope to see you soon. Hit the subscribe and then share the videos. Comment what you feel like we need to be clarified on.
Shalom.